What I want to get back to is doing more than just the expected value, because that here is maybe even good enough, because the difference between what we observe as open reading frames and actual genomes and this expected value is so large that you can possibly stop there and say, it's qualitatively so big a difference, I'm not going to do real statistics. But suppose we want to do real statistics and calculate the probability that we see such a large reading frame under the null model. A nice general tool to get more information about the distribution are these probability generating functions. We defined them last time already, so I'm going to quickly over. If you have some random variable and it has non-negative integer values only, then you can write this kind of series. Could be infinite or could be finite, both works. And that's a formal power series, or you can also say it's a representation of a function in terms of its power series. And so that's a function in some variable set. We'll mostly treat it as a symbolic object, and that's where we left off. One convenient thing is to compute the expected value of such a variable. If you have the probability generating function in a convenient form, that's easier to do than from scratch, because you can just take the derivative with respect to z. It's only one variable, so just the ordinary derivative and then set z to 1. And that's going to give you the expected value. And here's the proof. It's a very simple calculation. All you need to know is that the derivative of a sum is the sum of the derivatives. And that means we take the derivative inside the sum here of each of these terms. And that gives us precisely this formula. Once you set z to 1, that one just goes away. So if I was to insert 1 here instead of the general set after taking the derivative, then this goes away. So the whole thing is kind of just gone. If I strike it through, can you still see it? I think it's clear what happens. And then this is just the definition of the expected value if you keep the whole thing with the sum in front. So that's cute, but maybe not so exciting, because we knew how to get expected values even before this. The nice thing is it also works for other moments, and we'll look at the variance as an example. And there, the formula looks a bit more annoying to memorize, but maybe you don't even have to. The kind of trick that happens is the very same. If I take my my derivative here, but now I take the second derivative of this inner part, just the summands. Well, I can't do this really in one shot, but we have the first ones here, so it's not too bad to do. That's just a constant factor if you look at it as a function of z. Same for the k. Now we have another polynomial. Essentially, that's going to be the same pattern. And I guess technically this is only true if k is greater or equal to. For the smaller ones, we don't need to worry, because then there's a factor of 0 in front and the whole thing is 0. Right? For those small powers of k, the factor in front will kill the thing. Okay. So if you sum up just this part, so again, if you set z to 1, this part goes away, and we have the probability to have value k, and then we have something that looks similar-ish to variance, but not quite what we would want for the variance is, you can say it's the expected value of x minus its expectation squared. So we sum over all possible values for k. Say k greater equals 0 again. Probability for x to be k. And then this lovely thing. And we already know what this is, right? This is exactly this term. So that you can insert. And the easiest now is to move backwards. If we look at this term on the right, let's expand this one more step. Okay, I'm gonna write it again. And we have k squared minus k 2k ex minus ex squared. Then you can expand this one out. That goes completely out of the formula. This last command doesn't depend on e of x. This is a constant, so it can go outside. So here we have the k squared. Here's the k. That's a plus. And here, this is already easy. It's summing probabilities, so that's going to sum to 1. Okay, let me check. So this one's our expectation again, right? So we have 1 ex squared minus 2 ex squared. That leaves us with the 1 minus ex squared. And this one, we can split up again to look a bit more like this one. K squared is the same as k times k minus 1 plus 1 plus k. And that's where we have another e of x from. Okay. Maybe there's a more elegant way to do it without as much calculation. The nice thing about this taking derivatives of the probability generating function is it generalizes to higher moments without much problems. As long as you can take derivatives, the rest is just some rote calculation. We'll leave it with expectation and variance. Then you can use typical statistics on it, or you can use Chebyshev inequality to get bounds on large deviations, these kind of things. You look at that in the tutorials a bit. Let's also look at some example for a concrete distribution where maybe I can convince you better that it can be convenient to use these generating functions. So sorry, there's the view part on the slides missing and that I didn't copy. Good. We don't want to do this from scratch. I'm sorry. There was this question from last time that essentially will be answered in the tutorials. That's better. So while we're there, this depends a bit on your assumption. One or the other could be more sensible. And I think there's no definitive answer that says one or the other is more correct. It depends what you assume, whether you can reliably with the start codon detect the right position, or if you also have to live with the fact that it might be offset and you still want to define reading frames. So you look at both options. I did the one in lecture that gives the more interesting math. As you'll see in the tutorials, the other one is easier to deal with. Okay, with the slides that have the update that is not online yet, I don't have to write this example from scratch. I'll use this notation throughout. So uniform and then the set just means the uniform distribution over this discrete finite set. Here it's the first n integers where obviously we start counting at 0. So every value with probability 1 over n. Then the probability generating function is just a polynomial. It's a finite sum of powers of z. And the common factor, the probability is always 1 over n. So I can write this like that. Now that's just by definition. The power of this comes in because I can do algebraic reformulations of this term. In particular, just in case people might have forgotten about this, there's the TCS cheat sheet, and there's a formula for summing up powers from 0 to n, so that's exactly the form we need. And if you do that here, take these, the first n powers, so the formula on the sheet went until n, so I had an n plus 1 here. In our case, it's even more convenient. It stops exactly at n. So we can rewrite this sum in closed form, okay? So it's shorter to type. And now we can take, for example, the derivative of this thing, set it to 1, or I take the limit as set goes to 1, and retrieve, ta-da, the expected value of a uniform distribution. What is a little less easy to do in your head is the variance. I can never remember. I always have to look this one up. But if you're, say, stuck in a lecture room and would have to reconstruct it, that would be the one that I think is most foolproof, so that you can do it without making calculation errors. Okay, let me, just for the sake of the argument, show that you can do this in SymPy if you wanted. It's the same I started with before. That's this one. So just to show you that very little code suffices, is a little bit of a plug for Python here. There's this symbolic computation module in Python, and we import some functions that we're using here in the next few cells. You have to define symbols. That's what you're working with in the formula, but then you can write down terms in a very natural form, like this generating function here. You just express it as a standard Python expression. And you can take derivatives and you can set things to 1 with the subs function that we've seen last time and is used here as well. Now, if you do this in this one, you get a 0 by 0 because you have this set minus 1. There's a root in the denominator and a root in the numerator, but they actually cancel if you look at it carefully. A simple way to do this is to compute limits, which SymPy also is, for these simple cases, is doing very well. I'm just showing this also to educate you about tools that are convenient to use. And you can take derivatives twice, add the expectation, subtract the square of the expectation. That's just from this variable here. And then you get the variance of the uniform distribution of the first n integers. Okay? I find this cool. I don't know if enthusiasm sprang over. There's one more cool thing that I wanted to show. This is, if you have the probability generating function of some random variables, you can, and they're independent, stochastically independent, you can get the generating function of the sum of the two very simply as the product of the generating functions. If you write this down, this is nothing but the convolution. So what does it mean to multiply products of this form? Let's take the symbolic general form. I have two generating functions. They'll be of this form for some sequences, AK, BK. The product is also a series. And at the kth term, it has a sum of all the options how I can build K. And think about this as the finite case, two polynomials. You multiply every combination of terms, and you combine all of the terms where the resulting power is exactly K. Right? So you can have from the first series one contribution set to the L, then you get AL, and you multiply that by BK minus L. And that's one of the terms that you're summing up for the resulting sum where the power of set is K. In a way, this is just the definition of how you multiply power series anyways. It follows from the usual laws of how we do this for finite cases. And it works just the same if the sums are infinite series. And for the probability generating functions, what you get here, AL and BK minus L, that's the probability that X is equal to L. That's the probability that Y is equal to K minus L. If they're independent, then the probability that they jointly have these two values factors, and then you get exactly that this is the probability for X to be L and Y to be K minus L. Of course, then their sum is K. And there's you sum up over all different options for the value of X, say. Okay. Simple. That formula is also somewhere on the cheat sheet, if you can't remember it. Let's do a quick example here as well. This one I also find very useful to memorize stuff. Say you have Bernoulli random variables, so just coin flips with a bias, so they come up with probability P to be 1 and 0 otherwise. Then the probability generating function of this simple coin flip is very easy. P times Z for the one case and the other case. Now, standard binomial distributed variables are the sum of n of these things. And that means independent Bernoulli trials, I should stress. This is not on the slide anywhere. Okay. I guess all need to be mutually independent. But standard stuff, I'm not telling you much new. The probability generating function of this binomial random variable, though, is then the product of all these individual ones. The product of these is all the same, so it's just the nth power of that generating function. Okay. I rewrote this here so that it's clearer how you take derivatives, because that's of course what we want to do next. If you want to compute the expected value of y, I know that's a bit silly, you just want to go via the definition, but you could just take the derivative in this guy and set to 1. So what you get is the inner derivative is p, and the outer derivative is the n, the power goes down, and then the inner with power n minus 1. If you set to 1 in this one, you notice the p here and the minus p always cancel, and you get a 1 to some power, which just goes away. So n times p, as is obvious from the stochastic representation, the expected value of one of the xi's is p, and we got the sum of n independent copies. Okay, that's not hard to do otherwise, but the variance I can never quite remember, and you don't have to. You can take the formula from before. If you take the second derivative and plug in, then you get this lovely term, and the other two are the expectation minus expectation squared. And you can rewrite this in the somewhat more typical form, n times p times q, when you set q to 1 minus p. That's the one I learned in school. Yeah, maybe in school, I don't know. Also here, very briefly, like it's a proof of concept. There's the calculation, and you can even you can use simplify to do the combination of terms I showed you. Simplify immediately gives this representation as the shortest. Okay. That's all on the generating functions that directly connects, that directly like goes from the definition. I promised that we come back to this automaton. So let me take a copy of this one. Doesn't work. We can apply the same approach that we did for the expectation with the full distribution. If we say that our x and then the state, say p for prefix, that is now the generating function of the number of steps from this state till you reach an absorbing state. Let me write that down. It's the probability generating function of the number of steps x is a strange letter. Let's say this is the number of steps as the random variable to some absorbing state. And that's a random variable now. And we could say gp of z as the generating function. Of this guy. And then you can do the same kind of reasoning as before. Let me do an example. So the GUAA, which is an absorbing state, there's no further steps to be taken. So it's the deterministic constant 0, which means the probability generating function is just a 1, z to the 0. And let's do the UA, for example. Maybe this doesn't need to be quite as small. If you look at the UA, there's some chance with probability 1/2 it goes to one of these absorbing states, but let's write it down explicitly. So we do one more step. There was a +1 in the original formulation. Now we have to treat this as the sum of two independent random variables, one of which is the deterministic constant 1, and the other is as many steps as I'm taking from the target state. So the constant 1 has a generating function of just z to the power 1. The product of the probability generating functions corresponds to the sum, so I'm multiplying. And here I'm going to just take GUAA. That's what I get in this first case. Then I get symmetrically for the second UAG. Now I know it's silly, these are just one, I could have inserted them straight away. But here, this is showing the general pattern. If you go with a U back to this place, then you get the same pattern and just there's a GU now instead of this one. And the last term goes back to the start state. And you see how you can read this off from the automaton without thinking, like the first part here is even the same all the time. Okay. So you can equally form a system of equations. Don't be scared because there's a variable set flying around. It's not biting. You can just symbolically solve the equation the same way. And you'll get some solution for the G epsilon as a function of Z. All the others can be eliminated because you have as many equations as variables. So you can determine the exact representation for all of the states, but we're interested in the one from the start state. Again, this I prepared. So here's the full list of equations. Is again written in this SymPy convention where an equation has to be rewritten so that the right-hand side is 0, and then you just give the left-hand side. That's the start state. And I'm subtracting, well, there's 1/4 chance of going to U, and there's 3/4 of a chance of staying in the start state. And you can check in the automaton that that's what happened. Let's do the UA one was the one we did. You really see how these are very irregular and they're essentially just giving the automaton edges. If you solve that, that's the same code as last time, so I'm not going to explain the SymPy specifics again. There's a solve function where you give equations and variables, and then you can get the solution is a map from the symbols to the solutions. What we care about is the one for t. So it's t as a function of z. You can set to 1. What should be the result of this one? Double checking if people are here. That's the solution for the probability generating function of the start state. So the number of steps we take from the start state. But I'm just inserting z equals to 1. So that thing will just sum up all the probabilities. So it has to be 1. If I substitute 0, I guess I get the probability that it takes 0 steps. It should be 0 in this case, because from the start state we have to take at least 1 step. Then we can take derivatives and insert 1 in the derivative. That gives us the expected value. That's what we already know, but we should double check. And then we can take the second derivative and compute the variance. I don't know why this is underlined. I think the code runs fine. This is the generating function. The way it's determined, it's from a set of linear equations, so it's always going to be a rational function. This is maybe not so obvious, but you can prove this is always leading to a function polynomial divided by another polynomial. And these are very tame to work with, but we're not going to dig deeper into this here. So t of 1 was 1, summing up all the probabilities. Probability to use 0 steps was 0, as we said. That's the expected value, same as we had last time, if you look it up. And the variance is, well, whatever, some number. But more intuitive, I think, is the standard deviation. And so if you do this cowboy statistics of saying expected value plus minus 1 standard deviation is a reasonable confidence interval, then you're still far away, like you're still within a couple of dozen bases in an open reading frame of a random DNA, far away from the length of actual genes, which was usually thousands of bases.